Hello, my name is Doljan and today I am going to teach you the Ford-Fulkerson algorithm by taking you through a step-by-step example. This is a method for computing the maximum for flow, the network which is just graph whose edges have a capacity for flow. Maximum flow is simply the maximum amount of something, anything really, that you can move from starting node to an ending node. When you learn about Ford-Fulkerson, you may hear terms like minimum cut and residual graph. To reiterate, we're trying to find the maximum flow from a search node to a think node. We'll do this by finding augmenting paths from the search to the seek. An augmenting path is a simple path whose edges are either non-full and forward or not empty and backward. Basically, a path that's still a capacity for flow. You will see exactly what I mean by this in the example. Here is the flow network we use. S will be your source and the T our sink. We'll start by setting the flow to 0. The number on the left is the current flow sound edge and the number on the right is the total capacity for flow. We're ready to start. Here's how we'll do this at each iteration. We'll first find the path and compute the bottleneck capacity, which is simply the edge in the part with the smallest capacity, and finally we'll augment our path. We'll repeat these 3 steps until we can't find an augment path. Let's start at that and look for a path to T, remembering the edges in our path must be non-full and forward or non-empty and backward. Let's choose the following path for the bottleneck capacity. Then second, a value of 8. We'll augment all edges with this value. Also note that each node must remain in equilibrium, that in the flow into the nodes must equal the flow out the node we're done augmenting. So let's look for our next part. This looks like a good one. The bottleneck capacity is 2 in this case because the HDT only has a capacity of 2. Let's update the flow with this value onto the next pass. I'm going to specifically choose a pass with the backwards edge. So you can see how the algorithm works in this case. Note that our path includes going from D to even, though the edge itself is direction from A to D. This is what I mean by a backwards edge. Also notice D2 is not empty. So if we push 4 units from C to D, we can take away 4 units from D to a 4, being the bottleneck capacity we reserve. From edge a B. This may seem confusing, but just remember that each node must remain in equilibrium. In other words, while we add flow to our forward edges in the past, we take away flow from the backward edges. Let's look for another path. This looks like a good one. In this case, edge S2 provides our bottleneck capacity with the value of 2. We update our flow. Again, let's search for a path and augment the flow. We now have a flow value of 19. One more time, let's search for a path. Looking at S to A, we can see the path is full. Now looking at this, we notice we have a capacity of 1. However, the forward edge CD is full and the backwards edge CA is empty, so we cannot augment the path. Since we cannot find the path from S to T, our algorithm is done and our final flow value is 19. Don't be worried if you choose different paths, and I did that perfectly fine. Just make sure you end up with the same flow of 19 when you code this algorithm. You likely use the path first search at each iteration to find your path. I won't go into depth on the time complexity, but just think that at each iteration you will need to do a depth first search, which has a complexity of big O of E. In addition, the Maximum number of iterations is the total flow value. This will happen if you only update the flow by a value of 1. Each time this gives us a complexity of big O of 8 times F. Thank you for your watching this video. Goodbye.